Okay, so again, this example here, I'm going to use as a helpful guide for your MATLAB assignment number 4. As you're aware, the MATLAB assignments are 3 and 4 posted, and they will be due on Friday, April 23rd at midnight. Okay, okay. So in this case, this is a little different than the previous example. The previous example, our discrete dynamical system dealt with populations of a predator and a prey. In this case, we are going to let the vector x sub j, or x sub k, be the populations of juveniles, subadults, those are like teenagers, and adult populations of the spotted owl in Willow Creek, California. And here we're given what's called a stage matrix, And we want to know, what does this predict about the spotted owl population for the future? So we're always very concerned about what's going to happen to the future of populations of species. Okay. By the way, is this a stochastic matrix? This matrix here? Is the matrix, say, a stochastic matrix? That's right, Justin. No, it's not. Because the columns, for a stochastic matrix, you'd have to have the columns, the entries in the columns would all have to, well, each column, the entries in each column would have to add up to what? They'd have to add up to 1. Good, good. Okay, so let's go ahead here, and I think it would be helpful to interpret, though, what these entries mean. Okay, so let's go then to the next page. Are there any questions so far? Okay, so okay, here is the stage matrix, and it's a stage matrix because you go, juveniles to subadult to adults. Now, in the first column, the 0.30 here means that 30% of juveniles survive each year to become adults. That's what that means. Okay. Why, though, can't you go? I notice we have a 0 here in the first column from in that spot there. Okay, so why would that be 0? I mean, why is this value 0? So they're saying here, well, I mean, what does this 0 represent? It's, okay, that's right. Good, Benjamin. So after a year, that's right, Haley. Excellent, excellent. You can't, after a year, a juvenile cannot stay a juvenile. Okay, the juvenile after 1 year has to grow to be a subadult. Okay, and that's gonna, and 30% of juveniles survive each year to become subadults. Why can't, why do we have a 0 in this spot in the first column? Can a juvenile, so, this can't happen, right? Juvenile to juvenile. Can a juvenile after a year become an adult? Good, Ariana, you're right. They're not, no, that can't, after a year, a juvenile can grow to be a subadult, but it can't grow to be an adult. That would take how many years? Well, it would take 2 years. That's right. That's right, Peter. Good, good, Peter. Good, Haley. So, all right. Now, of course, subadults, okay, 71, well, um, hold on here. I think I have a typo here. This shouldn't be juveniles. This should be subadults, right? 71% of subadults. Please correct that in your notes, class. 71% of subadults survive each year to be counted as adults. Now it's interesting. 30% of the juveniles survive each year to become subadults, and then 71% of subadults survive each year to become adults. I wonder why the percentage of 71% is higher. Why do you think that is? That's right, Haley. Juveniles are more vulnerable to predators and things like that, getting injured and so forth. So this all makes perfect sense. This all makes perfect sense. We should have an intuitive feel for these values. Now the 0.94 here, this 0.94 right here, simply means that 94% of adults will survive and stay the next year. They stay as adults. And then this value up here, 0.33, well, hey, what's that mean? An adult can't become a juvenile, but adults can give birth to juveniles. So essentially, the 0.33 means that 33 juveniles are born each year to 100 adults. So essentially, the adults become juveniles in the sense that they give birth to juveniles, you see? Are there any questions so far? So it appears that only the adults can mate to give birth to juveniles. Subadults don't mate yet, and that's probably because of there's probably territorial issues. How the animals are. They're always fighting over territory and mating rights and all that, and so the adults are tougher than the subadults. The subadults have to get a little bigger before they can mate and stuff like that. Okay, well now what's the next step here? What do we need to do next with this matrix A? What do we need to do next if we want to make predictions about spotted owl population for the future? What must we do? What must we find for the matrix A? We must find its eigenvalues, good, and eigenvectors. Okay, so this matrix, unlike the the matrices that you've had in homework, which you can work out and on the exam, where you can work out eigenvalues and eigenvectors by hand. this here we're going to use a computer for. It's always good to be able to, work some problems out by hand so that you understand the concepts. But here we're going to use MATLAB to help us. This would be very, very hard to work out by hand. So I'm going to use MATLAB, and this time I'm just going to use the eig command. I'm not going to use eig parentheses sim of a, because the eigenvectors that result are not going to be pretty. They're not going to be pretty no matter what. You could have very ugly fractions. It could be, so it's better just to use eig of a. And in this problem here, it turns out that, we have one real eigenvalue, lambda 1 equals 1.01, and then we have complex conjugate eigenvalues. Interesting, right? One real eigenvalue and complex conjugate eigenvalues. And if we set up the expression for the number of juvenile, subadults, and adult owl populations in the kth month, that would be given by this linear combination. And you notice I don't specify the eigenvectors. I just say, okay, C1 times 1.01 to the kth power times V1 plus C2 times the second eigenvalue to the kth power times V2 plus C3 times the third eigenvalue to the kth power times V3. I don't write down the eigenvectors. I'm not going to write those down yet, because I may not need all of those eigenvectors, you see? I may not need all of them. Okay, let me give you a moment to catch up here. Okay, so now let's take a look at this. Let's take a look at this. Okay, I have three terms. Here's term 1. Here's term 2. And here's term 3. Let's look at term 1, this first term. All right. C1 times 1.01 to the kth power times eigenvector V1. As k gets large, does the first term disappear or does it stay? When k is large, as we let k go to infinity, all right, Haley says the term stays. Why is that, Haley? Why is that? The first term does stay. It doesn't disappear. Excellent. The eigenvalue of 1.01 is greater than 1. So that term is not going to disappear. 1.01 to the kth power as k gets large, that term, that coefficient is not going to disappear. It's going to get larger and larger and larger. Are there any questions so far? Okay. Let's go ahead here and look at the second term here. Second term. Here the coefficient is negative 0.03 plus 0.26i to the kth power. Now, let me just show you something here. Okay, let me just show you something. One moment. Let me go to the whiteboard. I want to show you something here. Hold on. Right. So, okay, so we got negative 0.03 plus 0.26i to the kth power. So, you know, we can just write this out a little bit. Hold on here. Make sure you're seeing this well. Sometimes I'll go back and look at the, oh, okay, I'm right here, okay. Dot, dot, dot. Okay, so what I've written here is negative, I'm sorry, it's negative 0.03, right? Hold on. Haste makes waste. Come on, hit that button. And hold on. Let's try it. Now, why isn't this? Come on. Now my status. All right, hold on. Let's do it. Okay. Man, I think this would be. Okay, so this is k times. I'm multiplying negative 0.03 plus 0.26i by itself k times. What do you think this is going to go to? Hold on. I like to have things look nice. I like to have things look nice. What do you think that's going to go to as k goes to infinity? Let me ask you this. The modulus of our eigenvalue, which is the modulus of negative 0.3 plus 0.26i, okay. How do you find the modulus of a complex number? Do you remember? To find the modulus of a complex number, what's going to go here? What's going to go here? That's right, Nafani, a squared plus b squared. So this is going to be negative 0.03, and this is going to be 0.26. All right. And what can you tell me about the modulus? Well, let me ask you this. Oh, let me ask you this. I got it. I got something good here. Like, you know, remember, like this is the second eigenvalue here. But the first eigenvalue, which was 1.01, okay, the modulus of 1.01 is, well, 1.01 is the same as 1.01 plus 0 times I, right? Okay, so that complex number, a real number is a complex number as well. It's just a complex number where the I component is 0. The modulus for that is just going to be 1.01 squared plus 0 squared, and that equals 1.01, and that's greater than 1. So the modulus of a real eigenvalue is simply the eigenvalue itself. And when that modulus is greater than 1, we know that that term with that eigenvalue is not going to disappear from the iterative vector equation for x sub k. But the same rule applies with a complex eigenvalue. The modulus for a complex eigenvalue, okay, so the modulus for the real eigenvalue, which is the same as just the eigenvalue itself, when it's greater than 1, that eigenvalue, the term with that eigenvalue will not disappear from the the iteration for equation, or formula, I should say, for the vector x sub k. Okay, so, and if the modulus for the real eigenvalue, which is the real eigenvalue, if the modulus is less than 1, then the term would disappear as k gets large. Well, it's the same for complex eigenvalues. This complex eigenvalue, what can you tell me about its modulus? I'm not worried about computing all this. I just want to know, is this modulus going to be greater than 1 or less than 1? So is the modulus greater than 1 or less than 1 for that complex eigenvalue lambda 2? That's right, Nafani. That's right, Hung. It's less than 1. Less than 1. And so same rules apply. In that case, that term, the portion of the formula containing that eigenvalue would also disappear, would also approach 0, 0. It would disappear as k gets large. So what value would this then equal? What's this going to equal then? That eigenvalue, that complex eigenvalue, multiplied by itself k times. As k goes to infinity, that should equal what? What number should it equal? That's right. That's right, Hung. That's right, Nafani. 0. All right. Are there any questions on this? So what's going to happen is, you're going to have eigenvalues and eigenvectors. And some eigenvalues, like in MATLAB assignment number 4, are going to be complex. Some are going to be real. But the point is, any eigenvalue whose modulus, okay, is less than 1, that term disappears as k goes to infinity. That term disappears. Okay, if the modulus is greater than 1, then that term will not disappear. And so that being said, if I go back to the example here, let me just see here. So I think we're good. Let me go back to the example. Just give me a moment here. Share it. Take this off. So that being said, then of the terms 1, 2, and 3, in the formula for x sub k, term 1 stays. What's going to happen to term 2? What's it going to go to? As k gets large. What I'm trying to say, class, is as k goes to infinity, let's say this another way here. I want to make sure you're comfortable, so I'm taking my time with this. What does this term approach? What vector does the second term approach as k goes to infinity? By virtue of the fact that you have this coefficient raised to the kth power, and the eigenvalue has a modulus less than 1. What vector would, oh, that's right, have to go to the 0, 0 vector? Good, Nafani. That's what it has to do. Okay, similarly, the third term will also approach 0, 0 as k goes to infinity. Because negative 0.0, the eigenvalue negative 0.03 minus 0.26i, that also has a modulus less than 1. So therefore, in terms of the evolution of the system, the only important term to concern yourself with is the first term. The first term determines the behavior, the evolution of the system completely. You can ignore the other two terms when you're talking about the evolution of the system. And that's good, because we can't have complex numbers of juvenile subadults and adult owls, right? We can't have, you know, these two terms that disappear, these two terms, the second and third terms that disappear as k gets large, well, those terms are, you know, you're taking a complex number times a eigenvector, you're going to get a complex eigenvector, and we can't interpret that in terms of you know, real numbers of juveniles, subadults, and adults. Okay, so far are we good? This should be helpful for MATLAB assignment number 4. Are there any questions? Who's feeling good so far? Okay, Naima is excellent, Naima. I'm glad Naima's here. Natalie's here, and I knew that. Thank you, Natalie. Excellent. Okay, well then, let's proceed on. So, as k goes to infinity, the x sub k vector is going to be equal to approximately C1 times 1.01 to the kth power times the first eigenvector. Now what I do is I actually specify the first eigenvector, okay, because that's the one that's going to be relevant as k goes to infinity. And we note that when k is large, then the number of juveniles, subadults, and adults in the k plus first month would be approximately equal to 1.001 times the number of juveniles, subadults, and adult owls in the kth month. And therefore, that means eventually there's going to be a 1% yearly growth population of juveniles, subadults, and adults for this owl population. Okay, and so that gives us some optimism. Okay, but it's pretty tight, you know, it's pretty tight. It isn't like this population is growing at a 5% yearly growth rate. It's only growing at a 1% yearly growth rate. So, you know, we have to be careful to protect this spotted owl population. Okay, so that it can grow back it'll grow back slowly over time, but we, you know, perhaps we don't want to build any, you know, we don't want to destroy any more, like any forest land to build homes and things like that. We want to, you know, try to just not upset the balance here. Okay, how many like owls, by the way, spotted owls? How many are? I like owls. They can kind of turn their head almost 360 degrees, right? Isn't that true? Oh, Justin says on who you ask. Justin made a joke. Catherine knows what I'm talking about. Hum doesn't like owls too much. Okay, well, that's all right. You know, there are a lot of birds, right? Okay, now we can do more here. We can do more with this. Okay. Eventually, I'd like to know what's the ratio for juveniles to adults to subadults? What's the ratio for juveniles to adults to subadults? And for that information comes from the eigenvector. Okay, that comes from the eigenvector. And let me show you how to find that. And I know, you know, we won't have really time for classwork tonight. I do have the homework assignment for this 5.6 is posted, and it's due on Friday. You have 5.5 due on Wednesday. But you know, this is going to be helpful for your for MATLAB assignment 4, and it'll be, you know, it's good for the homework too. But may I go to the next page? We want to find the we want to see what the ratio is eventually for adults to juveniles to subadults, and that comes from the eigenvector. So who's ready to go to the next page? You let me know. Let me know when you're ready. Okay, name is good. Haley's good, excellent. All right. Peter's good, excellent. Eleni's good, excellent, excellent. Okay, well then let's move forward. So as k goes to infinity, we learned that x sub k, okay, is that vector of juvenile, subadult, and adult populations of owls in the kth month. That approximately equals C1 times 1.01 to the kth power times the eigenvector V1, which MATLAB gives you. But I gotta make this eigenvector, I gotta manipulate it so I can get out numbers that I can interpret. So I can determine the ratio of adults to juveniles to subadults. So what I do is I take the smallest number. And I'm gonna divide, factor out 1 over that smallest number. Okay, and then that I get this vector here with entries 3.3651 and 10.2844. Now the reason I did that is because I wanted to have a 1 here. I wanted to have a 1. That's the reason I did that. I want to have integers. I want to have integers in this vector. Okay, so I can determine the ratios. Now, what happens here is you notice that I have let me see. Hold on here. I have a C1 here, and I have a 1 over 0.0920. But if I multiply them together, I can just say, okay, well then I'll call that C2. C2 will equal C1 times 1 divided by 0.0920. In other words, C2, I'll just write it here. C2 is equal to C1 times 1 over 0.0920. All right, and it just makes the formula a little nicer. And then what I'm going to do is I'm going to factor out, well, I'm going to multiply through this vector by 3 and then divide by a third. You know, I can't change I don't want to change the vector. I kind of like it as is, but I want to have numbers in the first and, well, the third entry is pretty close to 10, okay? But the first entry, 3.365, I'd like that closer to an integer. So I notice 3.365 times 3 is basically equal to 10. Oh, well, it's 10.0904. And so now my vector that I have here, which consists of entries of 10.0904, 3, and 30.8532, that's a pretty nice eigenvector, pretty nice vector, okay? And then the 1/3 times the C2 here, okay, the 1/3 times the C2, I'll call C3. So C3 is equal to 1/3 times C2. And so now I have a very nice looking, rather nice looking expression for my x sub k when k is large. And based on my values here in the vector, which are almost all integers, you know, nothing's perfect, but I can say that eventually for every 31 adults, 30.8532 is almost equal to 30. It's approximately 31. For every 31 adults, there will be, I should probably, yeah, about 10 juveniles and 3 subadults. Okay. It doesn't matter what this coefficient is in front. Okay, it doesn't matter what the coefficient is in front of that vector. It doesn't change this ratio relationship between adults, juveniles, and subadults. It won't change that. Okay. And even if you give an initial condition on the starting amount of owls, of juveniles, subadult, and adult owls, with the initial condition, we could determine a value for C3. It doesn't matter. Okay. Okay, so far so good. Are there any? Let me give you a moment to copy and make sure you're comfortable. While you're copying, how many think this is just like the coolest, one of the coolest things you've ever learned in math? the fact that you can relate linear algebra to the evolution of a species and whether the species could become extinct or not. I mean, yeah, I mean, this is really amazing. Hung loves it. Haley loves the applications. Justin likes it. Okay. Absolutely. It is. It's just so fascinating. And the beauty is now with technology, we can do problems like this in the classroom. Okay, well now, we also would perhaps like to know eventually what percentage of the population of owls will be juveniles, what percentage of the population of owls would become subadults, and what percentage of the population of owls would be adults. What percentage eventually of the population of owls will be juveniles, what percentage will be subadults, what percentage will be adults. Okay, well, so again, that information, the answer to that comes from the eigenvector. Okay, I'm just hold on one moment. I'm just checking one thing, class. One moment. Let's check one thing real quick. Okay, so now, there's several ways to find these percentages. You could utilize this vector here if you wanted to, but you could also use the original eigenvector. You could utilize that. Okay, and if I mean, we could use this original eigenvector and go from there. Let me show you how. All right. May I go to the next page? We're good? All right. Well, let's focus on. Well, okay. Hold on. Let me ask you this. If I wanted to know eventually what percentage of the population of owls were going to be juveniles, okay, how could I use this vector to help me? And I'll give you a little hint here. Let me put the 10 point, hold on. Let's do it right. Let me put the 10.0904 in the numerator of a fraction. And I want to know what's going to go in the denominator of the fraction. What do you think would go in the denominator? To find the eventual percentage of juveniles in the owl population. We ought to be able to use this vector, right? Just like we used it to get the eventual ratios between the juveniles, adults, juveniles, subadults, and adults. I'll show you the answer because I know we're getting close to the end of class, but think about what must go there. Does anybody want to offer a that's right, Eleni, very good. We would have the 10. Well, yeah, you would have the 10.0904 plus the 3. Very good. Plus the 31. Okay. Again, you'd have the 10. I'm doing it quickly because we're short on time, but I mean, technically you'd have 10.0904. You would need to have 10.0904 plus 3 plus 30.8532. So this would be approximately your denominator. That's absolutely right. But of course, we don't have to use this vector here. It doesn't matter. We could use that vector, or we could use the original eigenvector. And that's what I did on the next page. I'm going to divide 0.3095 by the sum of those entries. And that's what I do. So eventually the population will consist of 0.3095 divided by the sum of the entries in the eigenvector. That'll get you 22.96% juveniles. And then for subadults, I'll divide the second entry in the eigenvector by the sum of all the entries. And that'll get you 6.83% subadults. And then finally, for the number of adults eventually in the AL population, I'll take the third entry, 0.9464, and divide by the total of the entries. Okay, and that gets you 70.21%. I mean it might seem a little strange because we're not using, you know, like integers. It's a little it's a little easier maybe to understand in terms of the vector with the integers or close to integers that we had, you know, the 10, the 3, and the 31. But it doesn't matter because it's still, I mean, these entries are just multiples of those entries. The 0.3095, the 0.0920, and the 0.9464 are just, you know, multiples of the values, the 10, the 3, and the 31, you know, that we had. I should say 10.0904, 3, and 30.8532. But I think you know what I mean. So I'm really trying to spell things out for you here. How many are feeling good? How many are feeling good with this? Okay, Lainey's feeling good. And Natalie, wonderful. Naima, excellent. I like this. I love hearing positive. Hung and Ariana, excellent, excellent. Do you have any questions? Okay, I'll stop the recording. Thank you, Haley.